Welcome back. This will be the last lecture for Unit 3 on acids and bases, and we're going to be talking about pH indicators and pOH. In your textbook, it's 231 to 243, and by the end of this lecture, you will be able to interpret the results of acid-base indicators, perform calculations involving the hydroxide ion, interpret the pOH scale and how it relates to the pH scale, and perform calculations involving pH and pOH. So the first thing we're going to talk about are indicators. Indicators are substances that you can put into an acid or a base of unknown pH, and the indicator will change the color. Based on that color, you'll be able to tell the pH of a acid or base. Now the pH range in this table actually tells you the range of pHs over which an indicator changes color. So for example, if we look at methyl violet here, it changes from yellow to blue. For solutions that are yellow, the pH is below 0.0. For solutions that are blue, the pH is above 1.6. It changes color between 0 and 1.6. So in between 0 and 1.6, the color is going to be a greenish color. If we take a look at something like bromothymol blue, just moving up the list a little bit, it says it goes from yellow to green to blue. The yellow is for pHs less than 6.0. The blue is for pHs that are greater than, pH greater than 7.6. If the pH is between 6.0 and 7.6, then the color is going to be green. So if the pH is between these two, the color will be green. So the numbers in the pH range, and sometimes students get confused by this, it tells you the range over which the color of your indicator changes. It's not the limit of what the pH of what the indicator can do, it's the area over which it changes color. So here we have an example of just some solutions that have an indicator in them. And if we take a look, we're going to use these three solutions have had bromothymol blue added to them. The middle three solutions have had phenolphthalein added to them. And the last three solutions have had methyl orange added to them. And so based on the color, we're going to say what the pH range is. And it's always going to be a range. It's never going to be a specific number because the color is good for a range of color or a range of pHs. So if we look at bromothymol blue, the first solution here is yellow. And if we take a look at our indicator acid-base chart in your data booklet, it's page 10. And it's the same page for either the 2003 or 2008 data book. And we see that it changes from yellow to blue. It's yellow when the pH is less than 6. So for this solution, the pH is less than 6. It changes from yellow to blue, so we know that the pH of the last solution is greater than 7.6. The middle solution is green, so bromothymol blue changes colors between 6 and 7.6. So in this case, for the middle solution, the pH is, we'll put it in the middle here, we know it's got to be greater than 6, but it's going to be less than 7.6. If we move over to the next one, phenolphthalein, we see that there's a clear, kind of a light pink color and a dark pink color. So for phenolphthalein, it goes from colorless to pink. This one's colorless, so we know that the pH is less than 8.2. The one on the right is definitely pink, so we know this pH is definitely greater than 10.0. And the middle solution, it's pinkish or turning pink, so its pH, it's going to be greater than 8.2, but less than 10.0. And so hopefully you're getting the hang of this, and we'll look at the last set of solutions here for methyl orange. And for methyl orange, it goes from red to yellow. So this one is our red. It's a little orangey, but it's methyl. Oh, sorry, I gotta make sure I got the right one, because there's methyl orange. Oh, methyl orange, that's the one we're looking for. So this is the version of red that they're talking about. So this pH is definitely less than 3.2. The pH of the other end is going to be greater than 4.4. That's a yellow color for methyl orange. And the middle one is going to be in between the two. So I'll put my pH down, and it's going to be greater than 3.2, but less than 4.4. And so that's how indicators are used, and how to read the pH from a color. Other types of ways of measuring pH, there are pH meters that you can actually just stick into a solution, and the pH is given on a digital or analog, usually digital now, meter. There's pH paper that has a variety of indicators on it, and so based on the color that the paper turns, you can read the pH. So you basically get, if you take a look at this one here, it's a little strip of paper, and when you stick it into the pH meter, you can compare it to the colors that are on the wheel and get a pH from that. And then there's even pH paper that gets you a little bit more specific by having a bunch of indicators, and this way you can match 4 indicators. When all 4 indicators match the 4 colors on the box, you can get a pretty accurate idea as to what the pH is. So there's a variety of ways of finding pH. And so we've talked about pH and how pH communicates acidity. There's something related to it called pOH, and it's not used very much in terms of industry or in daily life, because it's really just the inverse of, or the reverse or the opposite of the pH scale. And what it does is it communicates alkalinity or basicity. So pOH measures the hydroxide concentration in a solution. So just as the concentration of hydronium can be converted to a pH, the concentration of hydroxide ions can be converted to a pOH. And so same formula as the pH formula, only put in some OHs instead of some H3Os. And same thing for the inverse log formula. So we'll just do a couple of examples just to get our feet wet. If a solute determined, we want to determine the concentration of hydroxide ions of a solution with a pOH of 8.7. So we have the pOH. We're looking for the concentration of hydroxide, which is going to be equal to the inverse log of a negative pH. This means the same thing as 10 to the power of negative pH. In this case, it's going to be 10 to the power of negative 8.87. And we run it through our calculator, 8.87, and we get 1.3, and pOH follows the same rules as pH. This number only has 2 significant digits, so we only have 2 significant digits in our answer, so 1.3 times 10 to the negative 9 moles per liter. Now, just like the pH scale, a low pOH means it's basic. Alright, so a low pH means basic. Our pOH, a high pOH means acidic. And it's the same 14 points, same idea, it's a 14-point scale, so if the pOH is equal to 7, then we have a neutral solution. So it works the same way as the pH scale. High numbers mean kind of the opposite of what we're measuring. So this pOH is at 8.7. This solution would actually be an acid, because the pOH is above 7. So when we want to find pOH from the concentration of hydroxide ions, we want to find pOH, so pOH is equal to the negative log of the concentration of hydroxide ions. And we're missing a number here. Oh, there it is. Ha. So we'll just get that number in there. Negative log of 5.77 times 10 to the negative 2 moles per liter. Punch it in and we get 10 to the power of negative 2. And so our pOH is 1 point. And same idea, this number has 3 significant digits, so we need 3 digits after our decimal for pOH, so 239. And because the pOH is low, this is pOH, because it's low, this solution would be basic, and it would be very basic. We can also find pOH from dissolving a base in water. Here we have KOH being dissolved in water, and just like with acids, if we're dissolving a solid into water, we want to write down the reaction. Now, because this is an OH base, we can treat it as just a dissociation reaction. And that would be our reaction. And then we can put in our numbers where they best fit. So the mass they gave us is the mass of KOH, or potassium hydroxide, so the mass goes here, 0.500 grams. They told us the volume of water, so I'm going to put the volume by our OH, because when we calculate concentration of hydroxides, we need to know the volume of our solution. And so from this, we need to find pOH, which means what that's related to is the concentration of hydroxide ions. So what we're going to do is find the concentration of hydroxide and then calculate pOH. So the first thing we're going to do is we're going to find the number of moles of KOH, then determine the number of moles of OH, then we can finally determine the concentration of hydroxide, and then pOH. So now we have a plan. It's just a matter of acting on it. To get the number of moles of potassium hydroxide, we're going to need molar mass. So our molar mass is 56.11 grams per mole. And now we can start doing some calculations. So the formulas we're going to need are our molar mass formula, which is mass over moles, and we'll need our concentration formula, N over V, and we're going to need our pOH formula, the negative log of the concentration of OH. And I guess the only real trick here is to remember that concentration and square brackets mean the same thing. So the concentration of hydroxide can be represented by a couple of different symbols. Okay, so let's get started. First we need N of KOH. It's going to be mass over molar mass. So 0.5 grams divided by 56.11 grams per mole. And we get 0.0089. So 0.00891 moles. Now that we have the number of moles, we're going to find the number of moles of OH by taking our 0.00891 moles, multiply it by our mole ratio of 1 over 1, and so our moles don't change, or the number of moles don't change. Now we can find the concentration of OH, which is N over V. We have 0.00891 moles divided by our volume, 0.5 liters. And so our concentration is 0.0178 moles per liter. And now we can find our pOH. So pOH is equal to the negative log of 0.0178. And just remember, we're using all the digits in our calculator. So negative log of the whole answer from the previous question. And so our pOH is going to be 1 point. And here's where we've got to check our sig digs. We have 3 sig digs in our question, so we need 3 digits behind our decimal place. So 1.749. 749. That's the pOH of our solution. This should make sense. KOH is a very strong base, so it should have a very low pOH, and it does. Its pOH is just about 2, which is much lower than 7. So it's very basic. So our answer matches what we should expect. Similar question, even the same numbers. So we have the same mass of solute being dissolved in the same volume of water, but we're going to find out that we're going to get a much different pH if we follow our steps. The first step is barium hydroxide. And because it's a hydroxide base, we can just drop it in water. And the first thing we're going to do is we're going to check our solubility table and make sure that barium hydroxide actually dissolves. And if we take a look at our solubility table, page 6 of your data booklet, in the hydroxide column, at the bottom of the first row, we see barium there, which means it does dissolve. So we're going to get barium 2+ ions plus 2 hydroxide ions. Now we've got to put in our numbers. They gave us the mass of barium hydroxide, so we get 0.500 grams of barium hydroxide. I'm going to put my volume of water with my OH because we know that pOH is related to concentration. And because I need the number of moles, it's the same as the last question. I know I'm going to need the number of moles of barium hydroxide, so I'm going to get my molar mass. And the molar mass of barium hydroxide is 137.33 grams per mole. And same steps. One, we're going to find the N of barium hydroxide, or the number of moles of barium hydroxide. Then we're going to find the number of moles of hydroxide, the concentration of our hydroxide, and finally pOH. And for every time that you have to do more than one step, it doesn't hurt just to write down a quick little list of what you want to do, just to make sure you know why you're doing what you're doing. So first, and again, I'm going to write down my formulas here. Molar mass formula I'm going to have to use, concentration formula I'm going to have to use, and my pOH formula. There we go. Okay, so number of moles of barium hydroxide is going to be mass over molar mass, 0.5 grams divided by 137.33 grams per mole, and we get 0.00364 moles. We're going to take that and use our mole ratio to find the number of moles of hydroxide. 0.00364. This time our mole ratio is 2 to 1. For every 1 mole of barium hydroxide, we get 2 moles of hydroxide ions. So we actually have 0.00728 moles. And now we can find our concentration. And it doesn't matter which way you write it. We can say the concentration of hydroxide ions is equal to N over V. n being 0.00728 728 moles divided by 0.5 liters. And we get 0.0146 moles per liter. And then we can take that and find our pOH. So pOH is equal to negative log of 0.0146 so our pOH is 1 point, and again, sig digs, we have 3, so we need 3 digits behind our decimal, 837. So again, a very strong base. It should have a low pOH, and it does, so we should be happy, at least in terms of our answer making sense. So here we have a pOH of cesium hydroxide. We want to calculate the mass of cesium hydroxide dissolved in the sample. So the first thing we need is an equation. Always get that equation first so that we know what we're dealing with. So cesium hydroxide is, cesium is Cs, it's a 1 plus ion. So CsOH, and it was dissolved in water to form Cs plus ions plus OH ions. Now they told us pOH, so I'm going to put it under my hydroxide. pOH is 3.50, and they told us the size of the sample in terms of volume, so I'm going to put that under my OH as well. So 35.00 milliliters. We want to find the mass of cesium hydroxide. We want to find this mass. So in order to do that, we're probably going to need molar mass, so I'm going to calculate it just in case we do. And the molar mass of cesium hydroxide is 149.92. So 149.92 grams per mole. And now we got to make up a different plan because it's a different type of problem. We want to find mass, but in order to do that, we're going to need the number of moles of cesium hydroxide. And the only way we're going to get the number of moles of cesium hydroxide is if we find out how many moles of hydroxide ions we have. And that we can do because we can find the concentration. So now we've got to go backwards. The first thing we're going to do is find the concentration of hydroxide ions using our pOH. Once we find that, we can find the number of moles of hydroxide ions in our solution. Then we can find the number of moles of cesium hydroxide using our mole ratio. And finally, we can find the mass of cesium hydroxide. So we have a plan. It's just a matter of following the plan. So the concentration of hydroxide ions is equal to the inverse log, or 10 to the negative pOH. And so it's going to be 10 to the negative 3.50. And so we'll run that through our calculator. Second function log, negative 3.5. And we get 3.162. 3.162 times 10 to the negative 4. This is going to be moles per liter. Now that we have that, we can find the number of moles of OH. And I should have done it ahead of time, but I didn't. We're using our inverse of pH formula, 10 to the negative pH. Then we're going to need our concentration formula and our molar mass formula. And I like writing them down just so that I can make sure I get my units in the right spots. So N of OH is going to equal to CV. So the concentration of OH, and again, it doesn't matter which symbol you use. You can use the OH in brackets or the C. It means the same thing. We're going to multiply that by the number of, or our volume, there we go, 35 milliliters, which would be 0.035 liters. I should have put my V there, but that's okay. So 3.162 times 10 to the negative 4 moles per liter times 0.033 liters. 35 liters, sorry. 0.035 liters. And we get 1.11 times 10 to the negative 5 moles. We need to use our mole ratio now, so the number of moles of cesium hydroxide is equal to 1.11 times 10 to the negative 5 moles times 1 over 1. There's 1 mole of hydroxide produced when 1 mole of cesium hydroxide dissolves, so the number of moles don't change, times 10 to the negative 5 moles. And then finally we're going to do our mass calculation, and the mass of cesium hydroxide is going to be equal to mass times moles, or molar mass times moles I should say, so 149.92 grams per mole times our number of moles, 1.11 times 10 to the negative 5 moles. And we get 0.00166, and we need 3 sig digs. Oh, sorry, almost didn't get it right. Our pOH only has 2 significant digits. Our volume has 4, so we're only allowed 2 significant digits. So it's going to be 0.0017 grams or 1.7 milligrams, or 1.7 times 10 to negative 3 grams. This is probably the best choice just because it's the least amount of writing for your unit conversion. So, and it looks the best as well, I think. I think with scientific notation it looks more confusing than it needs to be. But anyways, there's our answer, and we'll keep on trucking. So, if we take a look at what happens, we talked about this a little bit for pH. The same rationale holds true for pOH. In a neutral solution, because a neutral solution contains only water molecules, occasionally 2 water molecules will hit, and you get hydroxide ions and hydronium ions. In neutral water, every time one water loses a hydrogen, another one has to gain it. So in neutral water, the concentration of hydronium and the concentration of hydroxide are always equal, and they'll both be 1.0 times 10 to the negative 7. This means in a neutral solution, the pH is equal to 7, and the pOH is equal to 7. Because for both calculations, it's just the negative log of our concentration. So if we calculate the pH and pOH of pure water, both would be the negative log of 1.0 times 10 to the negative 7 moles per liter. This is equal to our pH, because the concentration of hydronium is 1.0 times 10 to the negative 7. It's also going to be equal to our pOH, because this is the concentration of hydroxide as well. So in both situations, the pH is equal to 7, which is the same as the pOH in neutral water. Another way to look at this is to say that what would happen if we added the pH and the pOH? In neutral water, the pOH we said was 7. In neutral water, the pH was 7. So it turns out that when we add them, it's 14. And what this is going to do is it's going to give us a relationship. It turns out that the pOH plus the pH for any solution is going to be equal to 14. So if the pOH for a solution was 3, and we wanted to find the pH, we just subtract 3 from both sides, and the pH would be 11. Note that they tell us the same thing. If the pH is 11, this is a base. If the pOH is 3, it's also saying it's a base. So either way we get the same answer, it's just a way of converting between pH and pOH. And so that's what this slide says. If you take a look, here we have some very acidic solutions and some very basic solutions and a bunch of stuff in between. Here are some things we should note. When we look at the concentration of hydronium, very acidic solutions have a high concentration of hydronium. 1 mole per liter is pretty high. As we get less acidic, the concentration goes down. For every power of 10 that we go, the pH increases by 1. And remember that as pH increases, solutions become less acidic. Once they get past 7, they actually become basic. When we look at the pOH for the same solution, a solution that is very acidic is going to have a very high pOH. So something that has a pH of 0 is going to have a pOH of 14. This would mean, and it's not written on the table, but this would mean that the concentration of OH in this solution is going to be 0. And then it's going to be 14 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 moles per liter. Right? It's going to be the same thing that happened with our basic solution and our hydronium ions. So there's a relationship between the two. If we want to convert between the two, we can find the pH and then add or subtract it to 14 to get the pOH, and vice versa. So for any solution, as the concentration of hydronium ions increases, the pH increases and the pOH, or the pH decreases. Sorry, we'll try this again. As the concentration of hydronium ions increases, the pH decreases, it gets lower. Strongly acidic compounds have low pH, and the pOH increases. The pH scale is logarithmic, and the change of 1 pH unit represents a 10-fold change in acidity. So, we're going to do some calculations here, and what I would do, again, is I'd pause the slideshow, and I'll do the first one as an example, and then pause the show and do the second two and see if you get the right answers. So, for the first one, what we would do is if the pH is 6.88, then the pOH is going to be 14 minus pH, which is 14 minus 6.88. So it's going to be it'd help if the calculator was on. 14 minus 6.88, 7.12. To find the concentration of hydronium ions, we can do a couple of things, but the easiest is the negative log, 10 to the negative pH. So we're going to go, the pH is 6.88, so this would be 10 to the negative 6.88. And we get 1.3, and since we have two significant digits, that's all we're going to use. 1.3 times 10 to the negative 7. For the concentration of hydroxide ions, well, this is 10 to the negative pOH. And so it's going to be 10 to the negative 7.12. And so we get 7.6 times 10 to the negative 8. And these are moles per liter. So we'll just put the units up here so we don't have to put it in each box. So this is moles per liter. This would be moles per liter. And if it's an acid or a base now, both the pH and the pOH have to say the same thing. The acidity of our solution can't change just based on a calculation. So the pH is below 7, it's definitely an acid. The pOH is above 7, again, that means the same thing, it's definitely an acid. So now what I would do is pause the slideshow and see if you can get the next two. So here are the answers. This last compound is a base. And I'll just give you a quick rundown of how I got the answers. From my 8.4, I was able to calculate the pOH to be 13.08. I then used 14 minus the 13.08 to get my 0.92. For my 13.48, I did the negative log of 8.4 times 10 to negative 14. And again, same idea. My pH is below 7, my pOH is above 7. Both of those things tell me this solution is an acid. For the next one, I did a couple of different steps. The first step I did, because I like to find my pH first, 14 minus 3.11 to get my pH. For my concentration of hydronium ions, I used 10 to the negative pH, which would be 10.89. And for my concentration of hydroxide, I used 10 to the power of negative 3.11. And again, pH is high, so it's a base. A low pOH means the same thing, and our solution's a base. So we're going to calculate the concentration of hydroxide ions for a perchloric acid solution. And now, this is where it becomes really critical to write down your equation and make sure you know what it means. So perchloric acid is a strong acid, and when it goes in water, for all of our acids, we make them react with water. So HClO4 plus H2O, and it's a strong acid. Then we get ClO4 negative plus H3O plus. And now we want to find out the concentration of hydroxide when we have a 0.5 mole per liter solution of perchloric acid. And so they actually gave us a concentration of this, 5.0 times 10 to the negative 3 moles per liter. And we want to find the concentration of hydroxide ions. The problem is there aren't any hydroxide ions in my equation. So we have to figure out how we can relate the two. And here's how we're going to do it. In order to get our concentration of hydroxide, we could get that from a pOH. Now pOH is related to the concentration of hydroxide. In order to get that though, the relationship we're going to use is its relationship to pH. We know that pOH is 14 minus pH. And the reason we're going to use pH is because we have hydronium ions. Since we have hydronium ions, we can calculate pH. And we can get our concentration of hydronium ions from our concentration of acid, HClO4. So here I drew same idea as what we were doing before. I just wrote my plan kind of backwards. I started with what I needed, and then I did the steps backwards to figure out what I would have to get first. So step number 1, we're going to get our concentration of H3O plus. Now, because we have a 1-to-1 ratio, so our concentration of HClO4 is at a 1-to-1 ratio with the concentration of H3O plus. In other words, for every 1 mole of perchloric acid, we get 1 mole of hydronium ions. The concentration of the two things are going to be equal. So we know that the concentration of hydronium ions is going to be 5.0 times 10 to the negative 3 moles per liter. Now from that we can get pH. We know that pH is the negative log of the concentration of hydronium ions. So it's going to be negative log of 5.0 times 10 to the negative 3 and so our pH is 2.30, and from that we can get pOH. So pOH is equal to 14 minus pH. So 14 minus 2.30 is equal to 11.70. And now that we have our pOH, we can calculate the concentration of hydroxide. So the concentration of hydroxide ions is equal to 10 to the negative pOH. I'll try that one more time. So 2.0 2.00, I only have 2 sig digs, so 2.0 times 10 to the negative 12 moles per liter. So there's our concentration of hydronium ions. Got one more example here. Here we have a solution of barium hydroxide, and we want to calculate the pH. And questions like this are pretty common. Generally speaking, we live in a world of pH. We don't really live in a world of pOH. So when we talk about bases, we generally want to know their pH because it's more intuitive to us. We've used pH more often, so we know what it means better. And so to find the pH, again, the first thing we're going to do is we're dissolving barium hydroxide. So we're going to write down what that looks like. So barium hydroxide, when it gets added to water, because it's an OH base, we can just dissolve it. And we get barium 2 plus 2 hydroxide ions. And now we can see what we can see. So first thing we notice is that we have 3 grams of barium hydroxide, a volume of solution 400 milliliters, so I'll put that under my hydroxide ions. And now what I want is pH. Now pH, the only thing in this formula related to pH or close to is my hydroxides. And remember, the pH, the only way we can find it is from pOH when we're dealing with a base. And so if we have OHs in our equation, we can only find pOH, and then we can find pH. So what we're going to do is we're going to find the molar mass of barium hydroxide, and then we can do kind of the same thing we did before. We're going to find number of moles of barium hydroxide. From that, we can find the number of moles of OH using our mole ratio. Once we get that, we're going to need our concentration of OH, and from that we can find our pOH. Once we get pOH, we can find pH. So there's our list of steps. And for this problem, we're going to need our molar mass formula, so I'll write that one down. We're going to need our, M over N, my bad. We're going to need our concentration formula. We're going to need, that's an N over V there, sorry. We're also going to need probably our negative log concentration of hydroxide ions. This is going to give us pH, or pOH. Once we find the pOH, we can use the pH plus pOH equals 14. So those are the formulas I'm going to need, and then it's just a matter of manipulating them the right way. So first we need the molar mass of barium hydroxide, and its molar mass is 171.35. And now we can start doing some real calculations here. So first, number of moles of barium hydroxide is equal to mass over molar mass. And we get 3.0 grams divided by 171.35 grams per mole. And we get 0.0175 moles. Then we need the number of moles of hydroxide ions, which is going to be our 0.0175 times 2 over 1. There's 2 moles of hydroxide produced for every 1 mole of barium hydroxide used, so times 2. And we get 0.035 0 moles. Now we're going to find our concentration. So our concentration of hydroxide is going to be N over V, 0.035 moles divided by 0.4 liters. And we get 0.0875 moles per liter. And from that we can find our pOH. So pOH is the negative log concentration of hydroxide, and so the negative log of 0.0875 and we get 1.058, and now we can find our pH. So pH is equal to 14 minus 1.058. So 12.94, we want 2 sig digs, so remember for pH and for pOH, it's only the digits after the decimal that are significant. So 12.94. There is our pH. Now we go back and we take a look. We have barium hydroxide. This is a strong base, so it should have a very high pH. We take a look at our answer. The pH is almost 13. That's pretty high. So our answer makes sense with what we expect, and we're good. So, lots of homework. A bunch of practice problems for calculations involving pH and pOH, and then the supplementary problems on page 753. Once you're done that, you are ready for the Chapter 6 test. Good luck.